Finally, we start. All right, guys. So we spoke about the idea of instantaneous velocity. So there is velocity and there is instantaneous velocity. And you want to think about those concepts very simply. So what is velocity? Do you remember? If you have uniform motion, that is constant motion, then that means that if you specify a given interval of time, let's say you specify 1 second, how do you compare which motion is faster, which is slower? If I move 2 meters a second, I am moving faster than if I move 1 meter a second. You understand? But if I just specify distance, obviously that's not going to convey the idea of speed, because I might say I moved 12 miles and you would say I moved 6 miles. There is no clarity who was moving faster, right? Clearly, if I moved 12 miles, I moved more. But maybe I moved 12 miles in 4 hours and you moved 6 miles in half an hour. You agree? So that's why we standardize. Do you understand why we divide? Why do when you all remember from elementary school that velocity is distance divided by time, but you have to know the concept. It's very important. The concept is why you divide by time. It's to standardize, to say in this amount of time, this distance has been traveled. Is that clear? And another thing that you should understand, when you take distance divided by time, you implicitly try to convey the idea that the motion is uniform. In other words, you don't speed up or slow down. Otherwise, that distance over time is somewhat meaningless. Oh, Angelo, I see you have a cat. That's pretty nice. That's wonderful.
I have too many cats.
Huh?
I have too many cats.
Too many. Well, we have the same problem. You probably are a philosopher, you know? Do you know, guys, the story about philosophers, right? A philosopher is a blind man in a dark room with no windows searching for a black cat that is not there, right? Of course, we might talk about it. If you're a mathematician, you ask, how many cats will you find? Okay? We'll talk about that. It's a very interesting idea. So, guys, back to velocity. You understand that when you say velocity is distance over time, you're implicitly suggesting that the motion is constant, right? Otherwise, that quantity is not that very sensible, okay? You can afterwards realize, you can say that's the average velocity. If I didn't track whether motion is constant or not, that will be called average velocity. But why average? For that, we need integration to understand, okay? It will relate to an average, like you add up a bunch of scores and divide by the total number of scores. But that's later. For now, think constant velocity means you travel a particular distance in a fixed interval of time. And that's a ratio. Ratio is expressed that you double the time, you double the distance. You half the time, you half the distance. Clear? Please confirm, guys, that at least this part is clear to you.
Yeah.
Sure.
Wonderful. Thank you so much. And if not, guys, again, we talk about it, right? Don't hesitate to speak about anything that ever makes you uncomfortable. The only thing I do not like is when I suppose you don't care, right? But or not honest. But other than that, I mean, you can ask me anything you feel inclined to try to ask. So what is, and could you tell me what is it that I'm observing? What is instantaneous velocity? Instantaneous velocity is what, my friends?
Is it a, like, that specific moment? Like,
yes, but it's a bit confusing. You see, guys, right? It's easy to forget. What do you mean in a particular moment? What's the velocity, right? Because in a particular moment, can I travel distance? It seems I cannot, right? If you give me no time, I will travel no distance. Do you agree? That seems intuitive to us, right? Maybe it's not true, but it seems that that's how we're built. This is a sort of observation about everyday life. So what is instantaneous velocity? Can you tell me what you look at to try to determine instantaneous velocity when you are inside a car? That's one easy way to think of it, I think.
The speedometer.
The speedometer, precisely, right? So instantaneous velocity is synonymous with speedometer, right? And of course, there could be, okay, Francis, this is just introduction to limits. You will see many questions about velocity once it becomes convenient. So that's just in physics. One reason that what we're talking about is important is to understand how to deal with velocity. Okay, Well, Christiana, Christiana is asking something interesting. Can we say instantaneous velocity is the velocity of an object in motion at a specific point of time? Christiana, you wrote something very philosophically interesting, but the problem is it is vague. You see, you have to make sure that it's not vague in your mind, because what is that? How do I measure it? What do I pay attention to? Okay, and the idea is that even if you do not see a speedometer, even if it's not in front of you, there is something in nature that will identify it. Okay, so the way we think here, look at it, that was the initial problem. Have you ever wondered, guys? I mean, have you ever wondered how a speed trap might work? Right? Speed trap. Like, you know, you receive a ticket, right? You go by a traffic light, and I can give you an idea of how it might work. Of course, it doesn't mean that that's the way it actually does, you see? I'll give you a very primitive idea of how it might work, and maybe the actual mechanism is more clever, right? What can you do with how do you tell some speed? Have you ever seen, some of you study biology, have you ever seen Venus flytrap? Have you? By the way, I have so many interesting biology questions for you if you study it, right? See how well you understand it. But have you ever seen a Venus flytrap? And do you know that when an insect lands on a Venus flytrap, the flower closes on the insect quickly, right? Now, there is a problem, guys, right? How would the trap close if the trap should not close if, let's say, a leaf fell on the flower? You agree? I mean, you don't want to trigger the trap. It's energy. It's basically it's costing energy to close the trap, right? And I think once it's closed, I'm not sure. Of course, you can tell me. I think once the Venus flytrap is closed, it will not open again. Yes. So tell me, please. Do you have an idea of what stops the trap from closing when something not animate, not alive, falls on the flower?
Does there have to be movement going on in a flower?
Yes, but how would that thing detect movement? Any ideas? So Francis, you say velocity, but be careful. You see a word velocity, you don't, you need to have a concept behind it. Once you have a clear concept, you can use the word velocity. We're trying to develop a concept. How would a mechanism work like this? So apparently the Venus flytrap has several sensors. You understand? Several sensors. It has, let's say, let's call it a trigger, right? One trigger, like a hair sticking out. If you touch this hair, and then in succession, rapidly afterwards touch another hair, it will close. You understand? So you set off one sensor and you set off another sensor in succession. If it's happening within a certain amount of time, the Venus flytrap will close. And that would be roughly how you can develop a speed trap. It's not the way it's developed, but here is a simple idea of how it might work, right? Like an action potential, sure. I mean, but again, those are big words. Let's talk simply. In mathematics, you talk very simply about something very complicated, because something very complicated tends to be very simple. Okay, so here, guys, do you see what happens with the car? I can imagine what I do is I set up a sensor here. So in other words, when the car drives over this point, let me just put a highlight. When the car drives over this point, imagine it's not the way it's done. You can do it with many systems, but imagine that you pass a certain point. It's a trigger. It starts the time, and by the other moment, let's say when you pass over here, you pass another trigger, and it ends time. The distance is known, right? The distance is known. So you might have something like a fixed distance, and then you have this would be t1, and this would be t2. So then you have distance t1 minus t2. Right?
So it's like the distance traveled between the 2 points in that period of time.
Yes. So you might fix the distance and you might divide by the change in time. If the change of time is very large, then the velocity is small because distance is divided by a large number. When, however, the difference in time is small, then you will get a big velocity. The point is a ratio, right? I mean, if the interval is short, then distance divided by a small number is a big number. Clear? Very easy, yes, guys? So that's one idea of how you make a speed trap. So this is now one concept. The second concept is how do I retrieve the actual velocity at a particular moment of time. If I took a photograph, let's say for this car at 2 seconds, the car is by the traffic light, right? And how would I know how fast it is traveling? If I have a recording of its full motion, I see the motion. It's recorded as a function xt. You understand what xt means? All it means is that at any given moment of time, the car has a definite position in space. You understand? Tell me, in other words, this is x of t is telling you where the car is at, let's say, t seconds in the video. So x of 2 is what? X of 2 is 5, meaning that at 2 seconds in the video, the car is in position 5 by the traffic light. So that's understandable, yes, guys? Correct? I mean, guys, I might over-explain,
Yeah.
but maybe I'm not. I mean, I have to be sure that you understand those supposedly basic ideas, which are not so basic. No, because I mean, because otherwise you would easily tell me how to calculate instantaneous velocity. So here is the problem, right, guys? So if you allow any duration of time, in that duration of time, you can experience changes. Do you agree? So for example, in 1 second, if you're moving, you can speed up or slow down. And even more so if you allow motion within 1 hour. So when I'm running, I usually begin running slower, then I accelerate, and then I slow down. You agree? So you never truly travel at a constant rate. It's basically impossible. You don't travel at a constant rate. So how do you adjust this idea? So what you can do is this. You understand that you are watching my face. And with each moment, there are changes. With each moment, I'm getting older. But you don't notice that, right? Well, because I look so wonderful. That's one reason why you don't notice it, right? Even though I'm 57 years old, but or much older, you decide. You don't notice that because, well, a second is a short duration of time. And in that duration of time, only little change happened. And some phenomena changes faster. So a second might be a long time. But the philosophy here is this. If you give very little amount of time for something to happen, then there will be very little change, right? Do you understand? So what we do, we are calculating average velocity, but if I want to know the instantaneous velocity at 2, I calculate the average velocity at a point near 2. You understand what I will do? I will select a point somewhere here, somewhere very close to 2. And the closer the better, because you understand, I mean, I do not know how fast this phenomena is changing, only that if I make that orange point very close to 2, there will be little time for change to happen. The closer the better. The closer that point is, this point, I call it 2 hat. For a moment, we'll give it another name, but I call it 2 hat. Do you understand why? 2 hat, because it's an imitation of 2. It's not a perfect 2. And then I get this interval. So all I'm doing, I'm calculating the average velocity or that distance over time thing, but where the interval of time is incredibly short. The shorter, the better, because then less change would have happened. You understand? And I will try to make it ideal. In other words, I will try to, it's called infinitesimal. I'll try to imagine that 2 hat is closer and closer and closer. We will talk about how to do that in a moment precisely. But the idea is, I do not know for this phenomena how short this interval should be for change not to happen or to happen very unnoticeably. Yes, it's representing a sort of strive to perfection. We will call it limbing. Yes, we'll call it limit because it's a sort of strive to perfection. You're trying to make 2 hat as best or as close to 2 as possible without it actually equaling 2. Yes. So you understand? So the formulas, if you understand that idea, you cannot forget instantaneous velocity. Formula is very obvious. How do you calculate distance? You take the difference of positions. So difference at 2 hat minus at 2. That will give me distance traveled, right? From this point to that point. 2 hat can be either above or below, it doesn't matter. Divided by 2 hat minus 2. Yes? That is the formula we obtained. You guys, you see why I'm explaining it so much? Because a lot of you say you would understand, but you do not come up with that formula. And that's trivial. This is just language-wise, you're saying distance divided by time. Good. So, and then how do we solve this, right? We figured out that the position function is t squared plus 1. It just fits the data. If let's say at time 0 the car is at 1, at time 1 the car is at 2, at time 2 the car is at 5, that just works. Look at it, because I have this. I have 0 squared plus 1 is a 1, right? I have 1 squared plus 1, that's 2. I have 2 squared plus 1, and that's 5. And I have 3 squared plus 1, and that's 10. So obviously those few values are not sufficient to be sure that I'm right, but definitely this position function seems to work, right? And so experimentally, supposedly we understood that from the video, the car is moving with position function x of t equal to t squared plus 1. Agreed? That's how I convert time to position. And so then let's calculate what we can do here, right? So we can say xt hat minus x of 2 divided by 2 hat minus 2. And I want to get rid of 2 hat minus 2 because it looks too much like 0, even though it's not a true 0, because 2 hat is not equal to 2, right? Remember, we spoke about division by 0. Actually, there were some very interesting people in my evening class, and they did not fully understand the discussion about 0. So if you're interested, guys, I can give you the nuts and bolts of real numbers. What are real numbers geometrically, from a geometric point of view, right? How did ancients figure out how to multiply numbers, or even how to take square roots? If you take a piece of rope, you can easily divide it in half, or an envelope, right? You can fold it and you can easily make 2 parts. But how do you make exactly 3 equal parts or 7 equal parts? Okay, the ancients could do that with relative ease, and if you're interested, I will explain to you what it is, and the way you can multiply numbers qualitatively without actually knowing the value of those numbers. The value of the numbers is just a code to communicate length. So if you're interested, stay after class. I can discuss that with you. I did it with a few students in the other class. Of course, we play one round of what, when, where to get you acquainted with the team. You know, we have really interesting questions there. Yesterday, some people couldn't leave and I had to translate like 7. But with you, we'll do 1. Okay, good. So here is what happens. Look at it, guys. 2 hat squared plus 1 is x of 2 hat minus 2 squared plus 1 divided by 2 hat minus 2. I simplify, I cancel the ones. You see, 1 minus 1 goes out, and I have 2 hat squared minus 2 divided by 2 hat minus 2. And here I use I factor out the difference of squares. Yes? Everybody remembers how to factor difference of squares, guys? Yes?
Yeah.
Yeah, this looks right. I'm just copying it all down.
Cool. Okay, good. Wonderful. So what we have is this, guys. It crosses out. 2 hat plus 2 is what remains in the numerator. Okay, so 2 hat plus 2 is essentially, and now look at it. And now because 2 hat is very close to 2, I recognize that my instantaneous velocity will be 4. Good. Wonderful. So nice. And look at it, guys. Instead of bothering to calculate it for 2 and 3 and other values separately, I can right away notice the rule. Look at it. If I want to calculate the instantaneous velocity, in other words, what is the speedometer pointing at, the arrow of the speedometer pointing at when the time is when the time is t? I can just calculate x of t hat minus x of t divided by t hat minus t. And when I simplify it out, I get t hat plus t, which is 2t. In other words, my prediction is that the velocity of this car at any given moment of time t is going to be twice that. In other words, at 0, it's 2 times 0, which is 0. At 0, it's not moving. It just starts accelerating. At 1 second, it's 2 meters per second. The speedometer is showing 2 meters per second. Yes. Noshin is asking an important question. What do the hat represent? Would anybody answer that? What is that hat represents? T hat is, what am I talking about? It's not a common notation. Sorry?
Is it the limit?
Well, let's not use that word because we haven't yet spoken about. Yes, so a fake one. Yes, France is a fake counterfeit number. What is T hat? It's something that looks like T. I'm trying to express this idea. It's essentially T, but not exactly T. Right? So 2 hat could be anything like maybe 2.0001 or 1.999, something that looks like 2, but not quite. You understand, guys? This is just language. The 2 hat. Remember this, right? So we have this situation. So my 2 hat would be something very close to 2. So I can have 2 hat something. For example, this could be 2 hat. And then that is my interval. You understand why I want 2 hat to be close to 2, guys? Would anybody explain to me again, just to be sure? Why am I picking 2 hat for that problem? Right? What am I trying to figure out? I'm trying to figure out something about this car. And why do I pick 2 hat?
You're trying to figure out the instantaneous velocity at that moment, so you want a point that's as close to the point that you want to examine. So you want to be as close as possible because the rate has changed.
Exactly. Guys, and you understand the philosophy? Do you understand the philosophy, guys? Is that I want to make this interval very short. Why do I want to make it short?
Professor, we also say like if we plug two 2's twice, like it's not gonna work. We will get 0. That's why we're trying to use the fake 2 to see what.
That's correct. That's correct. But one important thing that I want you to pay attention to, guys, is this, right? It's really philosophy we're doing. If you give some amount of time or a lot of time, you would have a lot of change. If you have very little time, you have very little change. You understand? So if this interval is very short, if the interval is very, very short, that means that, yes, if the interval is very short, that means that means that very little change, very little acceleration or deceleration happened. You agree? You see this point, yes, guys? It's not mathematical, it's a philosophical point. All right, guys. No worries, Junaid, don't worry. Okay. But you understand, guys, the philosophy is extremely important here, right? You forget formulas if you do not understand what they are motivated by. Good? All clear, yes, guys?
Yeah, sure.
It's 2 ideas, very simple, right? Is that if you have very little amount of time, you can calculate what you know as average velocity, and that will be very close to the actual velocity at that moment because there was very little change in time, and therefore very little possibility for acceleration. Good? That's as simple as it is. Beautiful. Would you like to work on a quick problem where you calculate instantaneous velocity on your own? Yes? Let's do it. Okay, here we go, guys. Here is a problem. So suppose that a particle moves with expression x of t equal to 5t squared minus 7. Yes? Let's actually make it minus 7t. plus 1. Let's make it a little harder. Okay, 5t squared minus 7t plus 1. And I want you to find one. What is the velocity at, well, the velocity at 1 second in the video? What's velocity 1 equal to? And more generally, if you feel comfortable, do number 2, because number 2 answers it for all values. What is in general velocity at any given time t? Okay, so I'll give you, well, I'll give you 5 minutes. Okay, 5 minutes from now. I hope it's enough time. And again, guys, if you are in a situation where you can turn the camera on, I would really appreciate looking at you. Well, exactly, Francis. How do you start this? That's why I explained it so many times, right? So that think carefully, very carefully. What is the idea, and how do I communicate this idea? What am I trying to attain? I'll show how to do it later. Yes, you guys, if you are ready, you can write your answer in chat, and you will see how I solve it, right? One thing that people sometimes do is that they work very hard where they shouldn't, and they work very little where they should. So you put a lot of effort in, let's say, simplifying the numbers or doing something like that. But the point is, you do exactly what you need and nothing more. I'll show you in a moment. And if you have the answer, you just type it in my... Sorry? Okay. Okay. All right, guys. I did not give you a lot of time, but look at it, guys. That's if you cannot solve it right away, that's a good idea to stay in office hours. You can practice and do it longer. You understand, guys? That one mistake that some people do, they kind of feel a bit upset and they think they want to quit early, right? But if you stay and do things on time, it will work amazingly well. Okay, so here is how we begin solving it. Let's say for v of 1. What am I going to calculate? What is, guys, v of 1? V of 1 is what? I mean, I need to calculate the position at 1 hat minus the position at 1 divided by 1 hat minus 1. I knew I need to do that for a very obvious reason. Is because I understand the philosophy, right? Because what is velocity, guys? You understand? It's nothing complicated. It's distance divided by time, just like you say. But speed actually changes all the time. So what I want to do is I want to create a very short interval. 1 hat is very close to 1. I want to know what the speedometer is showing at 1. So I select a number close to 1, and that is supposed to be a tiny interval, close to 1. You understand? And that means that there was little change where this particle could really speed up or slow down. And that means that a distance over time will be a good estimate of what the velocity is. Make sense? You understand what is the 1 hat? The 1 hat is as close as possible. It's conceptual. It's as close as possible to 1 as you can possibly obtain. In practice, it will be, if you're playing a video, if you're playing the YouTube video, you will select maybe the closest time interval you can to 1. You understand? You press play and you press pause. And you do that as quickly as you possibly can so that you create the smallest possible interval. So here is what we have, right? So remember the function, right? The function is what? So numerator is 5 times the number hat squared minus 7 times the number hat. And what did I write before? Let me see. It's plus 1, yes? Plus 1. You understand? This is just how the time is transferred to position. You see, Francis, how I started it? Yes, you see, it's just I plug in 1 hat into the function minus 1 at the function, which is 5 times 1 squared. Okay, where did I get 5 and 7? Well, look at it here. Do you see the 5 here? I just kind of came up with this. This is the position function. You see, this is what's given. You see, you observe the video by experimental experiments, or like we did, remember, in the previous case, or the formula is just given. You know something about the position. You need to know the position of the car for all moments of time to do the calculation. Okay, so because I recorded it on video, I can see the time bar and the position of the car all the time. Do you see that, guys? So that means that I know the position. And if I can come up with a formula, then I can do it algebraically. So it's 5 times 1 hat, times 1 squared minus 7 times 1 plus 1. Now, guys, you see, you could simplify things here, but that's not worth doing. Good? Yes, you understand what I did here? And I know many of you will start right away simplifying. You would say 5 minus 7. I don't bother doing it, and I will say explain to you why exactly. My goal is to cancel out 1 hat minus 1. So what am I going to do? I'm going to group like with like. So look at it. I can have this 5 square something. So I have 5 1 hat squared minus 5 times 1 squared. So I group this together, minus, we have here 7, 1 hat minus 1. And then the 1 minus 1 disappear. And what we are left here is this expression. This is what I call, this is just algebra, okay, guys? If you don't know algebra well, like this type of thing very well, then you need to practice, right? That's supposedly a prerequisite, but I will help you, of course, if you stay after class. That's just supposed to be immediate to you. You see what I do? I simply look at it, guys. You see, I take things that are alike and I group them together. Yes, I take things that are alike and I group them together. I take everything that is algebraically similar and I group it together. And that allows me to very quickly obtain the pattern that I need. Okay, so what do I get here? Now, this is simply 5 multiplied by 1. It's difference of square 1 hat minus 1. 1 hat plus 1. Minus 7, 1 hat minus 1, divided by 1 hat minus 1. And now if you remember your algebra, guys, I can simplify. I can cross this thing out. Again, everything I'm doing here is, you know, when you call it algebra, it's actually, it's just arithmetics. It's just, right? So what you have here is now, what remains is 5 multiplied by 1 hat plus 1 minus 7. And what is this? This is 10 minus 7. So 1 hat plus 1 is essentially 2. So it's 10 minus 7. And my prediction is that this equals to 3 meters per second, if that's how I measure speed. The speedometer at 1 is showing 3 meters per second. Now, you see, I wasted a lot of time doing it for 1. There is no reason, right? It's just as easy to do it for any moment of time t. How did you cross the 1 hat minus 1? Well, I factored it out. Look at it. I factor it out. You see, that's where factorization comes in handy. Let's see if you have that question once I do it generally. Okay, if I do it generally, see if you have the question, and then if definitely, guys, if you have longer questions, if you don't remember, if your algebra is rusty, you stay with me after class and we can practice that. Don't let it slide. So here is the general situation. V of t is x of t hat minus x of t divided by t hat minus t. This stage everybody understands. Yes, guys, not just because you just keep writing it, you might kind of decide to take a shortcut. I advise you not to do that. Like you think, okay, it's complicated, let me just remember this formula. The more you try to just remember without understanding, the harder it is to get a good grade, especially that the final, to prevent cheating, is conceptual. You understand? It's conceptual. In other words, it will not be a question where a computer can easily solve. So what you have here is, look at it, guys, let's do it. What is xt hat? Could anybody tell me what to write instead of xt hat?
5t hat squared.
Thank you. 5t hat squared minus 7t hat plus 1, right? I put it in parentheses, guys. Okay, I put in parentheses, and then for t, I write 5t squared minus 7t plus 1 divided by t hat minus t. Guys, if you are confused at any moment, let me know. All good? Up to this point, everything good?
Yeah.
Yes? Good?
Yes.
Yes, good, guys. And don't feel whatever you see. If you feel you don't understand something, no worries. Just let me know. Okay? And I will do my best to explain. In office hours, I can explain much slower. So now what do I do? Would anybody help me with the next step?
You factor out?
Yes, I factor out, but in particular, I would group like with like, right?
Yes.
So Right? Do you want me to do it slowly or I can do it fast? I'm not sure. Let me know. Should I do it step by step?
Yes, please.
Fast.
Okay. Okay. Somebody said step by step. So look at it, guys. Do you see that I see 5 something squared and here 5 something squared? So I hope you will. Do you understand this step, guys? So I write 5 and I can write this as t hat squared minus t squared. Do you understand what I did here? I basically grouped this expression with that expression and factored out the 5. Everybody with me?
Yes.
Yes. And then I do the same thing with 7. So I can take minus 7 and here I put t hat minus t. And I did the same. I grouped minus 7t hat with minus 7t and I factor the minus 7. And then, of course, I have the constant minus the constant is 0. I don't need to deal with it, right? 1 minus 1 is 0. So I have this expression divided by t hat minus t. Guys, do you all see that my goal is to get rid of the denominator? Because you see, I want to say that t hat is very close to t, but if I say it in this part, in this stage, then I get 0 on the denominator. I want to cancel it out so that I don't have to worry about it. I can cancel it out because it's not a true 0. It's very close to 0, but it's not a true 0. Good? So what do we get here? What is the difference of squares? So this is 5
T hat plus
t
T.
hat
and
minus t, t hat plus t. Yes, you can write it plus, doesn't matter in which order, right? This is this factored, right? Minus 7 t hat minus t divided by t hat minus t. Yes? Now, I will make this next step slightly slower. Do you see that I can factor out? Look at it, guys, right? I am going to factor this term and this term out. Factor it out so that I can cancel it, right? Some people forget how to do this type of cancellation. So let's see. So we have here 5 t hat plus t minus 7. And I factored out t hat minus t divided by t hat minus t. Do you see that step, guys? Look at it, it's here. You see, I factored what's red, I moved it outside so that you see it's, look at it. You see, if I were to FOIL, if I were to multiply t hat minus t back in, I will get the original expression, yes? And now at this step, I'm able to cross something out. I'm able to cross this and that out. Yeah? Wonderful. And so what am I getting? I'm getting 5 t hat plus t minus 7. And now look at it. What is now? I use this philosophy. T hat is kind of like t, right? So it's really the same thing as 5 times 2t. Very similar, I would say, right? 5 times 2t minus 7. So my prediction is that the instantaneous velocity will be 10t minus 7 for all moments of time, right? So now I can see if I plug t equal to 1 or t equal to 2, I have a formula for all of them. And so doing the problem right away abstractly saves you a lot of effort. You see, I would have never bothered solving 1. I would have solved 2 and then plugged in because I can, with the same amount of effort, get much more money for the buck. If that's how you say it, for your buck. Good? Clear?
Yes, sir. In this step, can we like simplify? If you go back, please.
Back here.
Yeah, like the last step. No, like the second one.
You mean on this board or on another one?
No, the other for number 2.
Okay, good. Here.
Yeah, like the last step. Can we simplify from here t hat minus t?
You mean not factor it out and just do one this right over here, just cross it out, right? You mean, if I understand you correctly, you mean just do this? Yes?
Correct, yeah.
Oh, obviously. I mean, I just try to explain in case some people forgot why you see, some people will do this. They will cancel this one with this one and leave this one intact. That's why I did it this extra step, so to remind people of the arithmetic. Okay? So you don't have to do, you have to understand, you do the minimum work possible as long as you operate conceptually. You understand? Much better than just stupid hard work is smart laziness. Okay? If you can figure something intelligent, something really clever, and get rid of those things and not do something, that's always good. But be clever. Okay?
Thank you.
Sure. All right, back to this lecture. We can do more examples like this if you want to train your hand.
Yeah, I'd like to try a couple more problems.
Yes. So that's what we do in Office. Okay, guys. Since so much material to go through, we can try in Office. You can see how it goes. Good. So there is this one here that I solved again. I solved 2 of them, and we can solve a few more. And again, guys, you don't have to worry. This will be revisited. This topic we will do many times. You see, we will go through the definition of the derivative, where you will do many such examples. But you can start now if you want. Okay, so here, what we are going to now do. So we have 2 notions in calculus for evaluating function. We can do several things. We can have a function and we plug in the number into it, or we calculate limits. So now we're talking about limits for the first time. Okay, limit as x goes to c of f of x. So what's the difference, guys? The difference is, in the first expression, you take the function and you push in one value. Whereas in this expression, what do? You take the function and you feed it successively better approximations of this number c, fake c. You understand? That's the c hat that you plug in. The limit is plugging c hat, except that you have to understand that c hat is not a number. C hat is a bunch of numbers, right? C hat is your best estimation of what c might be that is not equal to c. Okay, so you plug in, here is an illustration of how that works. Okay, guys, so here is a very simple function, f of x equal to 2 times x. Yes, if I plug in -1, I get 2 times -1, which is -2. What do I do when I plug in, when I calculate limit as x goes to -1? You see what I do? I will plug in a successively better and better imitations of -1. So here I decide to go from the left of -1. So -1.1 I plug in and I get -2.2. Here I plug -1.01 and I get this expression. And you see that as I plug in better imitations of -1, so this is what I refer to. So I refer to -1 hat. -1 hat as collectively the range of possible values that are very similar to -1. So it's a very sort of indefinite term. It's a very lax indefinite term representing -1 imitations. Good? Counterfeit -1s. So do you all understand, guys, what I do here with the limit? And notice the result ends up being the same. It ends up being, in this situation, in the limit I get -2, even though the process is very different. You understand? Limits can give you the same results as plugging in the value, but the process is entirely different. You see, plug in -1 into the function when it's possible, and that's just one plugin. When you take a limit, it's infinitely many plugins with which are trying to be better approximates of this value -1 in this case. Good? Everybody understands, guys? Limit is nothing so terrible, right? It's just, instead of plugging the actual thing, the -1, you plug ever better imitations of -1. And you can represent it at times in a table. Okay. Here is a somewhat artificial example. So this function is defined this way, guys. It's defined to be x squared plus 1 whenever x is not -1, and defined to be 3 when x is equal to -1. Yes? You see that, guys? You see this bottom expression? Tell me, please, what is f of -1 in this example? What is f of -1 that equals to? Precisely, that equals to 3. But what about this, guys? And what is the limit as x goes to -1 of f of x? What do you think that will lead to? If I take limit as x goes to -1, what will I get? Am I going to get -2?
Wouldn't be close to 0?
Well, let's look at it careful, right? So first of all, okay, what we're doing is what? When I say limit as x goes to -1 of f of x, could anybody tell me what will I be doing? Right? It's not only the answer that's important to us. The question is simple. We want to know the idea. When I take limit as x goes to -1, what will I be doing?
So let's say you get negative 0.99, and then you square it, and then you add +1.
Absolutely right. So, but it's more of a process, right? Not because minus 0.99 is some imitation of -1. There might be better. So what you do, you plug ever better imitations of -1, right? You can talk about it. I like the word blithely, right? Or blithely, right? In other words, happily careless, with indifferently, as plugging in -1 hat. You understand? And this is not a typical notation. -1 hat meaning plug in imitations of -1, and they should be as close to -1 as you possibly can get them. And it's rather clear that if you plug a number that is -1 like into x squared plus 1, you will get exactly Humira, but in the limit, you get ever better. You're striving to perfection, so you're gonna get the limit equal to 2. Do you agree? It's gonna be -1 squared plus 1, essentially, what you will be getting. Yes.
Yeah.
That's somewhat intuitive, I'm hoping. Of course, you can justify it later on. We're just getting an intuitive feel for what limits are. So I would say that the answer should be, that's how you write. Limit as x goes to -1 of f of x is 2. Let me show you through a sequence of steps. You want a break, guys? So somebody is exhausted. You want a short break?
No.
No, exactly. What a good answer, right? What a good answer. We never take a break, right?
You're provoking us, Professor.
Provoking? No, come on, guys. I am reasonable, right? We have a lot to study, certainly, but if you want a short break, 5 minutes or something, I'm happy to allow you to do that, right? Just let me know whenever you want something like that, okay? So no provocation, don't worry.
I'm just kidding. It's okay. Like we have to understand the topic.
Yes, but resting sometimes helps. But somebody asked it. I mean, what can I say? I mean, I don't need a break, you know. But if you do, you let me know. Right? Because we also have all of eternity to understand calculus. We go afterwards to office hours, right? We never leave. Eternity of calculus. So, guys, here is the situation. Do you see? So as Christiana said, you can see that you are plugging -99, -999, and 1, and you're plugging numbers that strive towards 1, and look what we obtain, right? The calculations seem to be similar to 2. You understand? You plug in counterfeits of -1, you get counterfeits of 2. And in the limit, you will not be able to distinguish between this expression and 2. But you understand, the point of this artificial example is that limits do not give you the same result necessarily as plugging in values. You understand? It could give, in this case, if I plug in -1, I get 3, but if I take the limit, I get 2. Right? It's a different process, and a different process may or may not give you the same result. Yes? So I actually think of very, how do you say, my analogies are visual for me. You understand? When I understand something, I try to get to the matter at hand, right? What is somebody talking about? So what I imagine is this, guys, you see? So my analogy, one of my analogies is that of a water gun. I'll give you other analogies if you want to. The other analogy is why not to get married. But one analogy is water gun. And this is what happens, guys. You see, so if you plug in if let's say the water gun is positioned over -1, I'm sorry, right? You can see that the point -1, it is going to be mapped towards 3. But imagine you put a plug at -1, and what you do is you have those, you see those blue brackets, right? You squeeze them. In other words, imagine you close the pipeline. The pipeline is squeezing, and as the pipeline is squeezing, the current of the water gushing out of the cannon is hopefully going to be narrow. It's going to get very narrow, and it's going to look like it's hitting just the number 2. You understand? Because what am I truly doing when I take limits? I plug all counterfeits to -1. And what is a counterfeit? A counterfeit is every number close to -1, excluding -1. So I have a plug at -1, and then and everywhere else, I'm just squirting all those particles. They are all entering the cannon. Of course, closeness is a dynamic idea here, right? Is that, I mean, this is somewhat close, but this is closer, this is closer. So the analogy is that imagine what you do is you're closing the faucet, or you're making the current very narrow, right? And you should imagine that this current is gonna get focused around 2. And that is the idea of delta epsilon arguments, which last class I tried to explain to students. I was able to do that, but it took me 3-4 lessons. And so for this, and it's always only for extra credit for the exams. So now I will relegate that. If you want, you can watch those videos, but I will relegate, or I can explain it to you slowly in office hours, but I will not explain it in class, even though understanding that is very, very good for the soul and for your mind, right? You have to really understand what is the limit. Why is it so nice and so trivial? Okay, so that is my water gun analogy. That's very good for delta epsilon, and I'll talk about it later. So guys, by the way, did you understand my water gun analogy, or you're completely lost? You have no idea what I'm talking about?
I've seen similar functions where it's like it curves and it almost hits a point, but it just like doesn't hit it. So that analogy was very good.
Well, you see, so in the limit, well, asymptote is just, we'll talk about what asymptotes are. I mean, just careful, guys, with the use of words, right? If you just name something, it doesn't mean you understood it. So there's nothing here that has to do with asymptotes. Look at it, guys. You see this table, there is something wrong about this table, because I'm only plugging in some select numbers, right? There are many, many numbers that are not in this table. In fact, if you actually study something about infinity, there are different sizes of infinity. So there's a huge size of numbers that were not represented in this table. Okay, so look at it. What do you do when you take limit as x goes to -1? You plug values near -1, not just near, but nearer and nearer, closer and closer. Yes. So what are you truly doing? You can imagine that, let's say a gun, if a function is a gun, it takes a particle on the x-axis, and its output f of x is a particle on the y-axis. It's where the particle hit. You understand? It's like a gun that you shoot a particle and you hit a wall. So I imagine that the x-axis is made out of water, and the gun is eating the particles and spitting them onto the y-axis, creating a water state. You understand? So for instance, right, let me just draw you this thing again. That's important for, well, no, let me do it. Let me draw you a water x-axis, you see? So this is a watery x-axis. And then there is the y-axis. Yes? And let's say, what is it that you are doing when you are trying to calculate? Let's say my function is f of x equal to x squared plus 1. Yes? X squared plus 1. What is it that you are doing when you calculate f of -1? What is f of -1? Well, arithmetically, you just take -1 squared plus 1, right? What is it that you're doing when you calculate it on the geometrically, right, in terms of the water gun analogy, that means that you are focusing your gun at -1, and this particle is fed in, and it flies towards the point 2. So 2 is f of 2. You agree? So when you calculate a function at a particular number, it's like you shot exactly one particle on the wall, right? Now, what will you be doing if you are trying to calculate limit as x goes to -1 of f of x? What is it that you're doing, guys? You're not plugging in -1, right? But you're plugging in nearby values. You agree? So what is nearby values? So let's say you open up an interval. This is nearby values, right? And you don't plug in this thing. So you plug in nearby values. All of the values in this interval. You agree? And what would happen is that you have those values going in all sorts of directions. Yes, but this is not exactly what we do with limit, because they are nearby, but we can get values closer, right? So I can then narrow the interval, and now I am here, and I can feed those values in, and then I'll get closer. Do you understand? So to say that the limit is equal to 2 is to claim that the water squirt, the stain on the wall, will get narrower and narrower about the point 2 on the y-axis. Do you agree? That's my water gun analogy. Do you understand it? So when I think of limits, I imagine that you place a water cannon over a particular particle and you're closing the water input. The input pipe is getting narrow. Here is the input pipe, right? It's getting very narrow. Clear? And this analogy is useful if you want to understand delta epsilon, of course, right? If you want to do the extra credit and if you want to train your mind to think mathematically. Right? I do not know, you see, some of you are taking a class to hopefully to just pass a hurdle. You want to pass a hurdle. You want to finish it, right? But for me, mathematics is a sort of dying attempt not to be a moron, right? Not to be an idiot, right? To be imaginative, to be thinking, to see relationships that in other subjects might not afford. I mean, it gives you such perspectives about life that other things rarely do, right? And you want to combine it, right? So you want to kind of combine it as part of your existence. So literature, mathematics, basically just make it all part of yourself. Okay, guys, so then let's talk about one-sided limits. Again, guys, if you are very tired and you need a short break, like 5-minute break, you just let me know. You can vote on it and I will give it to you. Of course, you're not confined to this chair, right? I'm not, well, I am a sadist, but not as bad as you imagine. Right? I am a sort of conscientious sadist. Anyhow, so one-sided limits. So you see on the real number line, I can approach the value c from either the left or from the right. And I indicate it by saying x is going to c with a minus on top or x going to c with a plus on top. This means what? That means that I am approaching from below c. The minus means that my approximations are less than c. And this means my approximations are slightly more than c. Yes? Good? Everybody understands? And of course, we will say that limit of f of x at c exists if the left and the right hand limits work. So here is an example, guys, right? So here is your next task. F of x is 2x if x is less than 3, 5 if x equals to 3, 3x if x is bigger than 3. Please calculate f of 3, the limit of 3 at the left and limit of 3 at right. So that's called right-handed and left-handed limit. Okay, thank you, Humaira. If at some point, guys, you need to stand up, or all I want from you is goodwill. That's all. Okay, so don't feel too threatened by me, unless you're malicious. Okay. Okay. So let's do this together, guys. Yes, it's simple enough. So what's the first thing? The first thing, f of 3 is very obvious. What's f of 3? Everyone, well, it's 5, right? If x is equal to 3, we get 5. So f of 3 is 5. Good?
Yeah.
Yes.
Yes, good. And what is f of x going to 3 minus? That's limit as x goes to 3 minus. If I approach 3 from below, I am using which formula? Look at it. There are 3 formulas. I use the top formula. Agreed?
QX, yes.
Yes, because if x is, this means that I'm plugging numbers that are below 3, which means I'm using the top formula. And the answer is 2 multiplied by 3 minus. If you want to, you can, of course, write that this is 6 minus. In other words, the number is always less than 6, but truly, you just write 6. You understand? There is only 0 plus and 0 minus where it can be important. Okay? In other words, this is an approximation of 6. If you say 6 minus, you're claiming the numbers you're obtaining are always slightly less than 6. Good? Now, if I take 3 plus here, that would be limit as x goes to 3 plus of 3x. You agree? Because x is bigger than, in this case, x is bigger than 3. So I use this equation, and I will get 9. Good?
Yes.
I get 9. 5, 6, and 9. Does limit as x goes to 3 of f of x exist? Is there a limit? No, the limit does not exist because we don't get the same value on the right and on the left. The left-handed limit and the right-handed limit both exist, but they don't have a combined formula. Yes? Very nice. And here is just, I mean, I did it here by a table, but you understand that table is somewhat misleading. It's a good way to begin to think about limits, but the table is only selecting, you see, maybe, what happens if I put 2.8, right? So, I mean, table can get me eventually, when you know enough to be scared of certain things, you can be paranoid, right? And so I prefer the water gun analogy, is that I select all sorts of values close by and I have a sort of reasoning. That's good. Makes sense. Yes, guys, it's just plug in. It's extremely simple, guys. You know, I mean, once you realize beyond the words, it's something very simple. You don't plug the number 3, you just plug numbers that are very close to 3. And of course, if you are this close to 3, you can get closer, you understand? So it's really like you're squeezing that pipe. So it's a motion that you can imagine, right? Like when you brushed your teeth and the water is flowing and then you're closing the faucet. That's what you imagine, right? And the water is dripping into the sinkhole, right? When it's exactly hitting the sinkhole, that's kind of the limit. Okay, so here is again definition. We say that the limit as x goes to c exists if the left and the right limits exist and they are equal to one another. That's obvious. And otherwise, we say that the limit doesn't exist. So the limit as x goes to 3 did not exist. Now, we do a little bit of limits on graphs. That's just again to illustrate the situation. Yes, guys? So we can think of a graph as a one-dimensional landscape. Maybe you don't believe it's one-dimensional, do you? Do you know what is dimension, guys? Right. So when you are walking around, what's the space of your movement is how many dimensions you think?
Three.
So let's see what you say, guys. Okay. So if you are walking around, in how many dimensions are you moving?
2, because you can't fly.
Exactly. What Liam answered it exactly. 2. You move in 3 dimensions only when you swim, I suppose, right? But you're moving in 2 dimensions because you cannot fly. Birds move in 3 dimensions. They can fly. Yes, well, you can jump. I mean, that's exactly, you're moving. Here is the thing, okay, guys? This is not important so much for this lecture, so forgive me if I mentioned that. That's kind of interesting, though, and that's investigation of how many dimensions are in space, like, and how many dimensions do we move. So look at it. You see, 1 dimension means that let's say you need to find an address. You know, you go to visit someone's house, right? I mean, you want to visit someone's house, your friend or whatnot, right? And if you are walking on a number line, so the number line has position 0, 1, 2, 3. Maybe the house is located in position 7. Do you agree? So how many numbers do you need to specify to tell the person where to go? Only 1 number. You just say go to 7, right? Now, if I take this number line and I make it curved, have you seen those bendable rulers, right? If it's a ruler, it's 1 dimension. Have you seen the bendable rulers? So you see, what is this? If I am attached to the graph, I can imagine this is 0, this is 1, this is 2, this is 3, 4, right? Maybe the house is here, right? You see, this is still 1 dimension. 1-dimensional. If you are attached to if you're confined in the space, it's 1-dimensional. It's just a bent number line. Now, the reason some of you might have said this is 2-dimensional is because you're observing that this 1-dimensional space is bending inside of a 2-dimensional framework. Yes, you're seeing this. It's a 1-dimensional space curved within a 2-dimensional space. Yes. And when you speak about space-time curvatures, what are you speaking about? You're speaking about precisely this, okay? So, so the way you are walking around, you're walking up and down, whatnot, but because you can control only your latitude and longitude, you're moving in 2 dimensions. It's just that your 2-dimensional space is folded within a 3-dimensional framework. You understand? Because you can only specify latitude and longitude, and your altitude is then given for you. But if you're a bird, you can move laterally. You can decide how high you go, to the right, forwards, to the right, or up, right? It's decided, right? But here, let's say, as soon as I know where I am relative to, let's say, the x-axis, if I know where I am relative to the x-axis, it automatically tells me where I stand. Okay, so my altitude is immediately specified once I specify position on the x-axis. So a graph in Calc 1 is 1-dimensional. Good. So this landscape is 1-dimensional. You see why? Because if I specify 0, I right away know how high you were. If it were 2-dimensional, specifying that you're over 0 will not tell me how high you are. Let's say on the y-axis, if I say the point 1, you can be anywhere in here. Right? That would be 2 dimensions. See? Let's say if I specify this point, you can be anywhere in here. That means your y-axis is free from the x-axis. Then you have 2 dimensions. But in this case, this doll is confined to walk on that landscape. So it means as soon as I specify the x-axis, its altitude is immediately known. So the doll controls only where it stands on the x-axis, only 1 dimension. Good? There are naturally very many problems. I mean, I can show you that that in some sense, every space might be 1-dimensional. So dimension is a sort of the minimal number of coordinates you need to specify to be able to locate yourself in space. So there are many interesting consequences of that, okay? But intuitively, this seems to be one-dimensional space. So here we go, right? So let's try to use this graph. This function is drawn. It's y equals f of x. And then tell me, please, by the graph, what do you think is f of 5 equal to? What happens if the doll is standing over 5? What happens to the doll?
It's at 2.
Well, but you see, there is a hole here, right?
Cannot see, Professor.
It cannot be standing there, or I mean, perhaps it's a sort of singularity. The doll disappears from existence, right? So it cannot be there. It's undefined, right? It goes, well, к чертовой матери, as they say in Russian, right? To the mother of the devil. Yes. So it doesn't exist. You understand? F of 5 is undefined. Clear? Now, please help me understand what would be the limit, though. X of x going to 5 minus and x going to 5 plus. What do you think is the limit?
2.
Precisely. You see, that means the doll can get closer and closer. It can if you're inching your way in this direction, it will be 5 plus, right? And that would be 2. Similarly, if you inch your way in this direction, you're descending towards 2, so that would be 2. Yes? Clear, guys? Notice the following. Look at it, that if x is approaching 5 from the right, it's always at 2. Its altitude is always 2. Whereas if you're going from the left, you are descending towards 2. So you're always at 2 plus of sorts, right? You're always above 2. 2 plus, right? You don't need to mention that, but that's just observation. And what is limit as x goes to 5?
2.
Exactly, 2. All good. So far easy, yes, guys? Okay, and this is just the same analogy. So you see x going to 5 minus is, I kind of say more than necessary. I say 2 plus, but you just say 2. 2 plus, I'm indicating you're always above 2, right? Okay. Now this one is a bit difficult to draw. This is a bit difficult to draw, but you know, I'll try to explain to you what it is. Mathematically, it exists for sure. Okay. So what happens as in this case, this is my new function here. What is f of minus 1? You think?
Nothing.
Well, there is a solid dot over here, right? So if you say basically you kind of sort of teleport. If you're at minus 1, you will be here.
Yeah, I missed the dot, so it's -2.
That's right. That's minus 2. Yes. Oh, interesting. Okay, and what about so f of minus 1 is -2. What can you say about the right-hand limit? Let's begin with the right-hand limit. What do you think is that going to be? Limit as x goes to -1 of f of x. What do you think it's going to be?
$1.5 because
That's right. It's all, of course, approximate. It's just intuitive. The idea is if you're saying x going to -1, you are walking the doll towards this location, yes, and it will not be standing on that hole because it's always to the right of the hole because x is to the right of -1. That's what we're saying here, right? So the result is 1.5. Now this is a little bit complicated. Do you see what would happen if I go on the left? If I put the doll here and I walk the doll towards -1 from the left, what will be happening here? What do you think? Of course, the drawing might not be, you might not understand the drawing. That's fine.
So there is no limit, Professor. It's like undefined.
That's right. That will be undefined. Do you see why, guys? Because you can create a function like this. It's what you do is you take a periodic wave and you can reflect it, for example, right? So that means that the doll would actually go faster and faster up and down like this, you see, forever. It'll go up and down. It'll get closer and closer on the x-axis, but it just keeps going up and down, so there is no limit. it diverges by oscillation. You see, I cannot draw infinitely many loops, but trust me, such loops exist. Okay, maybe I'll show you a picture. Let me see. Here, that's a picture of that situation. You see this? Why it's so solid dark? Because I mean, the waves, you see this wave, ooh, it gets completely compressed. You can create such a wave by mirroring. Just take sine and take a mirror, a spherical mirror, and that will look like that. Okay, so mathematically it's very possible. I cannot draw such things, obviously. You can see it gets like solid. You see, that's kind of like what happens here. You see? Amazing, isn't it? We will talk about such things later on. And what do you think is the limit as x goes to -1?
It doesn't exist.
Absolutely, it doesn't exist. Because one side works, the other side does not, right? So it doesn't exist. And then we have something known as infinite limits. Are you holding okay, guys? Still good? Not exhausted? Slept enough? So x going to 0, 1 over x squared. What is that going to be like? Let's try to understand by a table. Okay, if I go to 0, I can plug plus or minus imitations of 0. So let me start with plus or minus 1 over 10. So 1 over 10 squared is 100. Everybody sees that, guys? Do you understand what it means? I mean, my analogy is this, right? So in Texas, you have a lot of people who like to eat Texas size meals, right? So what is 1 over 10 here, right? So if I have something, let me just give you a simpler example. So right? So for example, if I do something like Angelo, what do you want to say?
No, I didn't mean to do that.
No worries. Limit as x goes to 0 of 1 over x, for example, 0 plus. Okay, so what is the 1 over x? Well, look at it. So I imagine it's like this. If it's 1 over 1, I think like this. I think 1 cake, and this I think 1 Texan. Oh, if you spell it correctly. So this is 1 cake per 1 Texan. The 1 Texan gets 1 cake. What do you think is this? What do you think that means? 1 over 1/2 means that 1 cake will be given to half of a Texan. So that means that the full Texan gets 2 cakes. You understand? So half of the Texan receives a full cake. Good? Do you understand, guys, why 1 over, let's say 1 over 10 is what?
10.
What is what? It's 10, yes. You see why? Because it means that 1 cake per 1/10 of one person, right? So it means the person receives 10 cakes. You can simplify it this way, okay? So that's what happens in this situation as well. You see this? 100, and then you have 100 squared, 100 cubed, and onwards, right? Sorry, 100 squared, it's all squared, right? You see this? So the way you express this is, look at it, as x approaches 0, 1 over x squared will approach the sideway 8. That means infinity. But I want to tell you right away that in our class, right, as far as calculus is concerned, this is not a number. You understand why it's not a number? This is just a vague indication of something like, imagine you have a balloon that you pump with water, and the balloon is expanding, and eventually the balloon is bigger than planet Earth, and eventually it's bigger than the solar system, right? And it just grows and grows and grows. This indicates growth without bound. You understand what I mean? Growth without bound. So it does not indicate precisely at what rate the growth without bound is taking place, but it's only growth without bound. So in our class, this limit does not exist. It has to be a number. This just means that the numbers are just getting larger and larger as I plug them in, right? So if I plug numbers close to C and I get larger and larger values and there is no end to how large they can get, I will say the limit is infinity. Or I would say the limit grows without bound. Understand? So you can say infinity, but be careful to remember that it's not a true infinity. It's like a shortcut. That's not a correct shortcut. It's not correct language. It's not infinity. At every moment, this is a finite quantity, right? It just gets
And
bigger and bigger.
this is a limit that exists, or does it not
This
exist?
does not exist.
Does not exist.
But
Okay.
you have to remember two things. It depends on the subject you're talking about, right? So in
Mhm.
calculus, right? I don't want to tell you more or too much, not to confuse you, but right now for our purposes, right? For our purposes, this means it's in complex analysis, it's very much a number, right? It's very much a number, and if somebody was interested, I can tell you about it in office hours, right? So for example, in some things that I am doing, here you can see this, right? You see this picture? So this point over here, the center, well, let's call it 0. It's not exactly 0, doesn't matter, but this is going to infinity, right? And infinity, it's somewhere very far out. It's actually a real point because I can just place the picture on a sphere. If you're interested in that analogy, I will explain to you what I mean, but after class. So in complex analysis, infinity is very much a point. But in our subject, infinity is not. Okay, infinity is just growth without bound. So we would say the limit does not exist here. Okay, you see what I mean? This is not infinity. This is just 100. What is it? 100. So 10,000 and million, and and bigger numbers. So at each instant, this quantity is large, but not infinite. It just approaches larger and larger. You see, it grows. Good. This is called growth without bound, but it's a long word, so you say goes to infinity. But it's really growth without bound, and the limit does not exist. Okay. So let's look at another question here. Find the limit as x goes to 3 plus of 2x over x minus 3. Okay. And the same thing for x going to 3 minus. Okay. So here I will introduce the idea of wishful thinking. Wishful thinking is this, guys. You see, you don't like that x minus 3 is in the denominator, and you would have preferred, you can factor the two, you would have preferred to see, ignore this last 3, you would have preferred to see x minus 3 over x minus 3. Do you agree? Because then it will cross out and be 1. So you see what I do? I factor out the 2 and I try to get rid of the denominator, and I write x minus 3 plus 3. And then I distribute the x minus 3. In here I get 1, and here is what I paid for. I got this 3 over x minus 3, and so when I multiply it through, I get 2 plus 6 over x minus 3. I can get it to that expression. Yes? Well, you don't have to do it necessarily for this question. I will do it two ways. I'm just showing you some sort of ways of reducing it and making it look like something else. That's when it's useful, right? When you try to simplify it. So what happens if you take 3 plus, in this case, this is 2 plus 6 divided by 0 plus. But you see, if you divide 6 by smaller and smaller positive numbers, you will get a huge number. So it will be like 2 plus infinity, which is infinity. So that limit is infinity. Okay, let me do it one more time without this process. Look at it. What will happen if I were to plug imitations of 3? If I were to plug 3 plus, look at it. If I were to plug 3 plus here, it would be 2 times 3 plus. So essentially it looks like 6, right? Divided by 3 plus minus 3. Now 3 plus minus 3 is 0 plus. In other words, you agree, 3 plus minus 3, it's something slightly bigger than 0. So it's like 6, essentially 6 plus divided by 0 plus. The 6 plus doesn't matter. It's close to 6 divided by a number very close to 0. And the result will be plus infinity. Do you agree? You see, because it's like 6 divided by 1 over 10, or 6 divided by 1 over 100, or by 1 over 1,000,000. You see? So that's the same as 6
6
times
divided by a really large number.
It's multiplied by a large number. Divided by small number means multiplied by a really, really large number. Good?
Right.
Guys, let me know. Do you understand it?
Yeah.
Yes. It sounds like a desperate kitten meow. Like, yeah. Right. I hope you understand it, guys. Yeah? It's not difficult. Yes? Yes. Yes, exactly. 0 plus is a quantity slightly more than 0. Good? Okay, so now can you carry out the same calculation without my help for x going to 3 minus? What is that going to be like?
Negative infinity.
That's right. It will be minus infinity for what reason? Look at it, guys. If I plug in a number close to 3, what I really have to pay attention is just the signs. A number close to 3, it would be like 2 times 3. 2 times 3 minus doesn't matter. And the denominator, it's like 3 minus minus 3. But 3 minus minus 3 is a negative number. So it's 0 minus. 0 minus. You see it? 0 minus. So it's 6 divided by 0 minus. So that would be minus infinity. It's negative because denominator is negative. You understand? At every moment, denominator is slightly less than 0. That's what I'm trying to say. Yes? All right. And this lecture is over. Limit laws. All right, guys. I will pause for 5 minutes to give you some rest. We have until 3:30, correct? So I make a pause of the video for 5 minutes. Remind me to record afterwards. Go breathe something, just drink something for a moment, and we will continue. Hello, guys. Are you back with me? Come here, come here. Hello. I'm recording. Thank you guys for reminding me. Recording has begun. I hope you rested a little bit. I know how exhausting it is to, I hope it's you're managing. I know how exhausting it is to do all of it at once. Yes, by the way, all right, let's get through it. We just have a few more minutes. And afterwards, if you want, stay for office hours. We can do like an hour or less than that. No, too much, Francis? Yeah, too much? It's okay. Then sometimes, guys, you can do the next thing. You see, I have office hours after the other class in the evening. You understand? You are all welcome visitors at any time. You agree? I am so happy to see you. I don't want to let you go. Some people never escape from me, as you can see, right? Once they are my students, they remain forever. I can show you a video of what happens to people. You know, they just disappear. I store them in my basement. Okay, let's get going with it. So delta epsilon is an argument that we will need to develop to prove those limits. But here we begin with something that seems extremely intuitive, right? So suppose that we know the limit of some function to be L and the limit of the other function to be M. Yes? What do you think will be the limit of the sum of those two functions? Well, you understand what happens here? As you plug numbers that are A-like into F, this expression looks like L, and this expression starts looking like M, right? Yes, guys? You all see that, right? You're seeing transformation. It's morphing. This f of x is morphing into L, and this g of x is morphing into M. Yes? So it's L plus M. And of course, f of x minus g of x will be L minus M. And if you multiply a constant times f of x is L-like number, so it will be C times L. Good. And the product is going to be L multiplied by M. Good. Okay, so and of course the most dangerous kind, guys, is the ratio of f to g. The limit is going to be L divided by M, but provided that denominator is not approaching 0. Because if denominator is approaching 0, you need to do further investigation. It can be all sorts of things. We will see examples. Good? Okay, guys, here we go. So here is a graph, right? Let's see if you can do it. Do you see the graph? So we have a graph for G, it's red, and the graph for F is blue. Could you please help me calculate number A, the limit as x goes to -2, fx plus 5gx. Calculate this one, please. You can do it. I believe in you. Do your best, guys. Oh, people are responding. Wonderful. Okay, beautiful, guys. So in this example, it's not even necessary to simplify it all, right? What happens? Look at it. What happens to f as x goes to -2? Look at it. Let's look at -2. It looks, it's kind of a bit weird looking, right? Let's say it looks like it will be 1, right? It looks like this is 1. So f looks like it approaches the number 1. Plus, what do we have here? What does g approach as we go to -2? It looks like we approach 2. So it's 5 times 2. And I agree with you. It looks like we will get, 11. Yes? Agreed? Looks like we have 11. And now it might be a bit more dangerous, guys. Can you solve B? Everybody understands the 11 part? Yes? All of you are seeing? No? Francis, no, tell me what bothers you. So you see how I do it. Look at it. I calculate if x goes to -2, what happens to the first function, right? It's really that what's happening is a transformation of f and a transformation of g. And I can see, well, you do not see the graph of f plus 5g. You only see the graph of g and the graph of f. Okay, look at it, guys. X goes to -2. What happens to this part? Just pay attention to what happens to this part. What's happening? It's a bit, so look at it. I walk x towards -2. So here, do you see my pen? I'm walking x on f towards -2. You see, Francis? I climb. It's very rough. You don't need to be. See, it looks like it would be 1. Yes, it looks like it would be 1. Agreed? Now I walk g towards -2. So here I am on the red curve, g towards -2. It's not defined to be this point, but I'm approaching this hole. So I'm approaching the number 2, right? So g approaches 2. You see, so if f approaches 1 and g approaches 2, then f plus 5 times g will approach 11. You all see that, guys? Yes, Francis? So it's, you understand, just what I imagine, just walking a doll here and I'm seeing what f is transforming in. It's like I imagine it's morphing like Play-Doh. It's becoming the number 1 for f, and g is morphing like Play-Doh and becoming the number 2. Yes? That's beautiful. Now, please explain to me, guys, what will be, if it exists or not, what's limit as x goes to 1 of f multiplied by g. Some of that might be a bit harder. F multiplied by g at 1. Be careful.
Professor, can we Can we calculate them like limit when x goes to 1 plus and 1 minus?
Of course, you're free to do that. This already means this is asking for 1 plus and 1 minus, right? So it only works if 1 plus and 1 minus don't give you different values. So that's precisely right. You try to calculate 1 plus, 1 minus to see what will that situation be. Okay, so one answer is -2, I presume for B. Does not exist, Christiana. Okay, good. So some people say -2. Christiana says does not exist. We will see what becomes of it. Okay, guys? By the way, guys, if you feel after this class fully exhausted and you want to go to office hours, again, I remind you that I teach another section of calculus. You're welcome to join any of my lessons. As I mentioned, probability, even if you can keep up, you're welcome there too. Does not exist, a few people say. So let's now analyze this carefully, guys, right? So what happens if I approach, let me follow Christiana's correct suggestion. So limit as x goes to 1, well, let's begin with 1 minus. 1 minus f, I will just make it f times g. I don't want to write the x, okay? It's shorter this way. It's called suppressing the x. Kind of like suppressing freedom of speech, but not as bad. Good. So we have what is that going to equal to, guys? Let's see. F as x goes to 1 minus, I am walking. You see where my pen is moving? You see it? Oh, where do I get? I'm walking it towards 1 with from the left. I'm getting to -2. So it's -2 multiplied by what will be happening to g as I walk towards 1. Well, it kind of looks like it would be 1. You agree? I mean, it's not well drawn, but let's say it's 1. Good? Good?
Yeah, sure.
Yes, France is good? Good. -2 times 1. Now, what happens if I carry a similar calculation and I say x is going to 1, but from the right of f multiplied by g? What do I get now? What is that going to be like?
-1.
-1, precisely, because look at it now. I walk f from the right of 1. You see, to the right of 1, I walk f where the cursor is taking me, and it's -1 times 1. So it looks like it's -1 times 1. So they are not the same. Do you agree? -2 is not the same as -1. And so what do I say here?
Limit does not exist.
Does not exist, and you can use this symbol if you prefer. Right? You can say does not exist or use something like that. Up to you. Wonderful. Now let's do C, guys. It's C. Try to see if you can calculate this one. Okay, Gian, thank you. Okay, the limit does not exist. Sometimes you can say a bit better than just doesn't exist. Okay, so let's now do it together. Good. So now we're approaching 2. Okay, we're approaching 2. So let's see what happens to the numerator. As f approaches 2, we get, it looks like we're getting the number 1, right? F looks like it will be at around number 1, but G will be around the number 0. So let's again break into left and right limits, okay? So let's consider limit as x goes to 2 from the left of f divided by g. I suppress the x to make it easier to write, okay? Now, what will that be? Let's now see f, when I approach the number 2, f looks like it's about 1, right? So, so it's about 1 divided by g. What does g become? I approach 2 from the left, so g is positive. So g is 0 plus. Do you agree? You see why it's 0 plus? Because g, when I'm to the left of 2, I'm somewhat above 0. I'm here on g, right? So 1 over 0 plus will be plus infinity. Yeah? Easy, right, guys? You see what it means? It means, does this limit exist? Let me just ask you. Is just the left-hand limit, does it exist?
No.
No, because what is that plus infinity? It means as you're what the 0 plus means, as you're plugging smaller and smaller positive numbers, the quantity gets larger and larger, but it doesn't approach a definite value. So it's not, the limit doesn't exist. It calls diverges. The limit diverges to infinity. That's how you say it. The numbers just grow without bound. Yes? So we will get plus infinity. What happens if I do the limit as x goes to 2 plus of fg? Well, numerator is still going to look like 1. Denominator is going to look like what? Exactly. Like 0 minus. Yes? Because look at it. If I'm to the right of 2, on the red curve is below the x-axis. Here, you see it? Negative. Negative, yes? So that is minus infinity. Good? Yes. Wonderful. So the limit does not exist. Even one-sided limit doesn't, but they are not approaching, you know, in one case, I am decreasing without bound. I get large numbers, but negative. Or here I'm increasing without bound. I get large positive numbers. Wonderful. Okay. And this is what we just did. Now, here is what the limit laws allow us to do. If I can prove that the limit laws are true, or if I at least can intuitively sense that they should be true, I can use them to generate a lot of limits and not carry calculations, so such complicated calculations. Very quickly figure out what the limit is. So for example, guys, as x goes to a of c, that's equal to c. Do you understand what that means? What is c? It's constant. In other words, let's say what is limit as x goes to 17 of 5? That's obviously just 5. Phi is not affected by what x is doing, right? Okay, so limit of a constant remains the constant. You agree? X is going to 17. The function, basically, what is this 5? The function is giving you the same thing. F of x equal to 5. That's the function. So if you plug f of 12, you are getting 5. If you plug f of minus 11, you're getting 5, right? You're always getting 5, no matter what you do. And of course, the limit is then not changing that. The limit is not changing any of that. And of course, another limit is very obvious. Limit as x goes to a of x, right? If x is becoming a, what is x becoming? It's becoming a. It's tautological limit. You agree? So far, so good, guys. And then look how easy it is then to calculate limit as x goes to a of x squared. Well, I can use the limit of product is the product of limits. If that statement is true, then it's limit of x multiplied by x, where x is one limit I know, and I can call it f, and it's here the other limit that I know, right? The limit of the product is the product of the limits, so that I expect to be a squared. Similarly with x cubed, I can break it into two parts. I already know that limit of x squared is the same as plugging in the value, right? So it will be a squared times a, which is a cubed. Guys, do you understand what I'm saying? Right? You see that I am referring to those laws which you can justify by delta epsilon. They are not some teacher did not come up with them and tell you just those are the laws you can use. They are true. If I know what is the limit of one function and I know what's the limit of the other function, I can easily find the limit of their sum. I can easily find the limit of their difference based on that law. You understand? I can easily find the scalar multiplication times this function or the product rule. Okay. In other words, if I know f becomes like the number L and g becomes like the number m, the limit of the product will be like the number Lm. You understand? That's an idea that if you think about it, it might be intuitive to you, it might not. You can prove it to be true if you bother justifying delta epsilon. Okay, you can prove that that is true. So assuming that works, look at it. It's very easy to calculate limit of x squared because I can take two functions. X squared is like x multiplied by x. You agree? I know the limit of this function. It's just obvious, right? Limit as x, if x is becoming a, this function will become a. This is the same thing, so this also will become a. So it will be a times a or a squared. If I know that for x squared, I can easily know that for x cubed because now I can write it as x squared times x. You see, I kind of break what I have, the new things I have in terms of previously solved problems. So it's a squared times a, which is a cubed. And in general, x to the n will approach a to the n by repeated application of the product rule. Now here is an example, guys. Okay, so calculate this limit as quickly as you can, and we will justify the steps that we're doing once, right? But eventually you understand what's going to happen, right? So this limit, what do you imagine this limit will do? If x is approaching 5, what do you think is going to be the solution? Okay, let's do number 8 together, guys. It's a bit tedious, but I would like to show you just how the limit laws are supposed to work and why it's pretty obvious what this limit is, right? So by the limit laws, I can just break it into additions and subtractions. You agree? It's just if I can figure out this limit and that limit, I will figure out the limit of the bunch. So I break it up, then I can factor out, from here I can factor out the scalar. I can factor this scalar out and blah, 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 blah. In this part I already know it's 5 squared, this is 5, and this is 4. Look at it, guys. The limit is the same as if I just plug in instead of x the number 5. The process is not the same, but the end result is the same for this example. Do you understand? Some people, when they're novice in calculus, they just eventually start saying just plug in the number 5. That's not the process. It just ends up being the same result as if you just plugged in the number 5 in this case. You see? And that's because of limit laws. Okay, you can actually for your, just when you're doing it at home, it's nice if you understand how the logic is structured, right? But you can also think intuitively. Look at it. I am squaring a number similar to 5. Here I am multiplying by a number similar to 5. So you expect the result to be similar to the counterfeit will function similarly to the actual number 5. So you expect the result to be the same as if you plug in 5. Do you agree? Right? Because the imitation of 5 is essentially doing the same work. So that's intuitive here, yes? Now help me with this one last problem, guys, and then we'll call it a day. What is the limit as x goes to -2 of this expression? Can you tell me what it is?
So Professor, we basically just follow the limit laws, right?
Absolutely, but so I hope that some of you are of the mind frame that you understand that those are laws that you need to prove, and the proofs are not trivial. They take some imagination to accomplish and some ideas. But of course, in some sense, the result that those proofs reach are intuitive. You expect them to be true because what you're doing here, you're plugging in a counterfeit number into an algebraic expression. You think that the counterfeit number will function similarly. So the result will be similar to plugging in the value. Okay. So truly, if you go and find limits in the wild, they are very dangerous, very scary, and very not intuitive. But because we know so few functions, initially there is very little difference in the results we get when we use limits and when we use when we use plugging in. So yes, I presume the answer is you just plug in -2 in here and in here, and nothing bad happens. You see, just there is a minus here. Do you see what ends up happening if you follow here? I just did it once to show you how I'm quoting laws. I'm showing you that if the laws are true, everything follows logically, right? So I can see that the result is -1/11, which will be the same as plugging in the number -2. Same result, but not the same process. Do you follow me, guys? Same result as plugging in -2, but not at all the same process. It will be important to understand. Yes. Okay. So in our class, we encounter simply a few things. Look at it. We essentially deal with polynomials and rational functions initially, and those are the simplest functions that are. I will explain to you what polynomials are and how important the idea of a polynomial is and what powerful tool it is if you understand how to harness this power. So guys, at this point, I will stop the recording and stop the lecture. And I will see you, well, you can stay with me a little bit if you want to practice some more exercises. And of course, if you want to see one what, when, where problem, right? We will do one what, where problem, see how good you are at those interesting problems, okay? I'm gonna stop the recording and we will play what, when, where, one question, and then we'll do some office hours if you want to do it.